Okay, so how's everybody feeling? Confident? Yeah, in the home stretch. Less than a month of lectures left. Only a couple of assignments left. So today I want to do a couple of things. I want to start on the topic of priority queues and show you actually one of the nicest results that I've ever seen in this area. In fact, it's one of the nicest data structures results that I've ever seen. But before that, so the last two assignments are available. Assignment 4 and Assignment 5 are on the course webpage. Assignment 4 is due soonish. So today's the day that I'll go over that. It's a little bit different than some of the other ones. So now's your chance to ask me questions. I will be away for a week starting this afternoon. So you'll have two guest lecturers, Daryl, who you've seen before, and Ahmad, who you may have seen as a TA for some course at some point. Okay, so assignment 4 is about drawing trees. So in particular, drawing binary trees. What you are given, or what you have to do, is write functions on a class called geometric tree. What's a geometric tree? Well, it's a tree whose vertices have x and y coordinates. It's a binary tree, not necessarily a binary search tree. And you have to assign x and y coordinates to the nodes so that when you draw the thing, it looks nice. And nice has different definitions for 3 different parts of this question. So the first one, so you don't have to worry about the user interface or making these pictures or anything. That's all done for you. All you have to do is write 3 functions that assign x and y coordinates to these nodes in a particular way. The first one is called in-order draw. So every tree it's a binary tree, a rooted ordered binary tree. So every node has a left child and a right child. And in order draw, you assign the y coordinates, and this is a computer graphics thing. So the y-axis points down, unlike all of mathematics. So you assign the y coordinates starting with the root at coordinate 0, the children of the root at coordinate 1, the grandchildren of the root at coordinate 2, and so on. So that the drawing is going down from the root. If you trace the path from the root, it's always going downwards. And the x coordinates are assigned so that everybody gets their own x coordinate. It's an integer. With the smallest being assigned 0, so the smallest coordinate that you assign is 0, and the largest coordinate that you assign is n minus 1, where n is the size of the tree. And they have this property that everything in every x coordinate in the left subtree is smaller than the x coordinate at the root, which is smaller than every x coordinate in the right subtree. So you get this nice drawing here of this tree, and if you think about it, that means that if you only focused on the x coordinates, this thing is a binary search tree for the x coordinates. So, and the y coordinates are just assigned nicely so that they show how far you are from the root, how deep something is in this tree. Is that clear what you're supposed to do there? So why these drawings look like this? There's 2 examples here, one with a strange sort of tree, one with a more complete binary tree. Yeah?
So it doesn't matter the value as long as it's greater or lesser than?
No. The values have to be the integers 0, 1, 2, 3, all the way up to n minus 1.
The x coordinates or the values in nodes?
Well, there's no values in the nodes. There's an x coordinate and a y coordinate at each node. And the x coordinates have to be 0 through n minus 1. The y coordinates have to be 0 through the height of the tree. So one thing to look out for is Again, this will go to an automated submission server, which is already up. The thing to look out for is you can have a picture that looks like it's right, but what the submission server is doing is not looking at the picture. It's running some examples and looking at the actual x and y coordinates assigned to the nodes. So things like being off by 1 will give you a picture that looks exactly right if you're not paying attention, but the server will treat as completely wrong because every x coordinate is wrong, for example. Okay, so that's the first one. That's called in-order draw. The next one is called leftist draw. So what does leftist draw do? The y-coordinates are assigned the same way as the previous one. So the y-coordinates are just the distance from the root of the tree. The x-coordinates, on the other hand, are packed in basically as small as possible without two nodes getting assigned the same x-coordinate. So if you imagine going through this tree level by level, starting at the root, well, the root gets an x-coordinate of 0. It's the only thing at the 0 level, so it's fine. The two children of the root get the x-coordinates 0 and 1. And even if there's only one child, it would get x-coordinate 0. And basically, as you cross each level, you assign the coordinates 0, 1, 2, 3, 4, 5, up to the size of the level minus 1. So it's packed as much as possible to the left. Okay. Is that clear? Okay. Good. So there's two examples here, one of a weird-looking tree and then one of the complete binary tree again. Complete binary tree, not a great drawing of that. The weird one, not so bad. And the final one is the trickiest and maybe that's the most complicated definition. So you think of it, the definition is recursive. So you start at the root, and the root has two subtrees, a left child and a right child. And one of those, either they're both the same size, in which case it doesn't matter, so they have the same number of nodes in each subtree, or one of them is smaller than the other. Okay, so if one of those is smaller than the other, you take that one, and you draw it. So this is the subtree of that thing. You draw it directly below the root node. Okay, so in this picture, this is the root node up on the top left. There's two subtrees. There's a pretty big one over here on the right, and there's a smaller one below. So the smaller subtree gets drawn directly below. So the root of that subtree goes directly below the root. You just add 1 to the y-coordinate of the root. That tells you the position of the root of this new subtree. And it's drawn recursively the same way. So you look at the smaller of those two children, the smaller one goes directly below. So if you look at this example, the root had two children. One had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes. The other one had 1, 2, 3, 4, 5. So the one with 5 got drawn below. If I look at this node, it has actually only one child. One of its subtrees is empty. The empty subtree got drawn below, and the larger subtree got drawn to the right. This one, again, has only one child, so the subtree of size 0 gets drawn below. And then this one has two children, and it doesn't matter. Each one has size 1, so one goes to the below and one goes to the right. Okay. So first thing you do is you draw the smaller subtree below the root. Now that drawing takes up some space. It takes up some y coordinates and it takes up some x coordinates. The other child, the larger child, gets drawn just far enough away that it goes past the largest x coordinate that you used on the smaller child. Okay. So here, when I drew this subtree, I used x coordinates 0, 1, 2, and 3. So the other child of the root gets x coordinate 4 in this case. So that's not the same as the number of nodes in this subtree. It's not, you can't calculate it by counting the number of nodes in this subtree. You really have to draw the whole subtree first, keep track of the largest x-coordinate that you used in that drawing, and then you can draw the right subtree, and you draw it starting here recursively. Okay. Now, one thing about this is it does not, I mean, these other two drawings preserve the order of left and right, so the left child gets drawn to the left and the right child gets drawn to the right. This third drawing doesn't do that. I can't tell by looking at this drawing which one is the left child and which one is the right child of the root. The smaller one is the one that's drawn below, whichever one that happens to be, either left or right. Okay. So any questions? Yep. So what do you mean? From the picture, I can't tell. I have no idea what the left and right children were.
I mean, from the algorithm.
Well, I mean, so the algorithm is just what I said. You look at the two sizes of the two subtrees, and the smaller one goes below, and the larger one is the one that goes to the right. And how far to the right, you don't know until you draw the smaller one below. All right. So a few things here. Although there's a little demonstration that comes with this. So in the archive, there's I'll show you two versions. There's the version you can download. And in there's a class called Geometric Tree Demo that opens up one of these little windows that looks like those examples I was showing you. So this is the version you download. There's the drawings of these trees that it's producing right now. There's some tree. Let's take a new complete binary tree. There's a drawing of that complete binary tree. I'll tell you what it's doing. It's assigning y-coordinates based on distance from the root. You can kind of see that. But the x-coordinates are actually assigned at random. So the tree has all kinds of crossings and garbage in it. So you need to do something other than that. And there's two kinds of trees, complete binary trees, and these things called Galton-Watson trees, which are sort of random trees. So let's take a look at those in a version that actually works. So there's an in-order drawing of the complete binary tree. And the Galton-Watson trees, sometimes you have to make a few tries because they're random and sometimes they're tiny. There's one Galton-Watson tree, in-order drawing of a Galton-Watson tree. We can try another one. There we get a tree with one node. Not only sometimes are they tiny, but sometimes they run away and get really big as well. So there's one that the drawing doesn't quite fit, but you can sort of see it's looks like it's doing the right thing. And that's the in-order drawing. The leftist drawing of that tree looks like that. And the balanced layout of that tree looks like that. Now, you don't have to worry about how any of that code works for the for displaying these things. All you have to do is write three functions. Here they are. In-order draw, which does the in-order drawing. Leftist draw, which does the leftist drawing, and balanced draw, which does the balanced drawing. And the first two are already half written. The y-coordinates are already assigned correctly for the first two. All you have to do is the x-coordinates. The last one takes a bit more work, the balance draw. Okay. And one thing that you will find is it's pretty easy, well, as is often the case on trees, it's pretty easy to write recursive versions of these functions that do what you want. If you're not careful when you do that, you will write functions that take a long time to execute on really large trees. So, for example, we won't display them, but the server will try trees with like 1 million nodes or 100,000 nodes. Try drawing them using your code. If you do things like, well, for instance, some of these things depend on the size of the two subtrees. The third one depends on knowing the size of the two subtrees. If you say, each time I need to know what the size of the two subtrees is, I'll just traverse the tree to compute its size, then what you'll find is it will be too slow, because not only will we test with very big trees, but we'll test with very unbalanced trees, including probably a tree that looks like this, but has 1 million nodes in it. And so if your balance draw function says, okay, to draw the root, I need to know the sizes of these two subtrees, so I'll call a function that computes the size of this tree and the size of this tree. Well, that function will return 0 very quickly here, and it'll return 999,999 for this node after traversing this whole tree. Now, if you do that recursively, that means this next time you do this, it's going to call a function that has to traverse this whole tree, and then a function that has to traverse this whole tree, and so on. So it's easy to get quadratic time algorithms. My suggestion is you use what you know about data structures to do something like, we already know how to compute all the sizes of all the subtrees in a tree using a recursive algorithm, and in fact, a little bit of digging around in the book, and you can even figure out how to do it with a non-recursive algorithm. And then just make a map. Then use a map that maps nodes onto the sizes of their subtrees, and then you have that information available afterwards whenever you need it. Yep.
In order to draw the first one.
Yep.
If you have a node that has a right subtree, the leftmost element of that subtree should never be a lower next node.
So that's this picture here. This is the leftmost node in the right subtree of the root. Okay. So not only should this thing be efficient, so we want basically all of these things should run in time that's O of n, so linear in the number of nodes in the tree. But part of that also means it has to be robust, and part of that means you have to be careful when using recursion. So not only will a recursive solution on a tree like this take a long time to run, actually, well, in this case, it won't take a long time to run. Why not? Yep. Because it will crash very quickly. So it doesn't take a long time. In fact, it very quickly crashes because this makes a recursive call, that makes a recursive call, that makes a recursive call, that makes a recursive call 1 million levels deep. Well, no programming language outside of Lisp can really handle that amount of recursion, and Lisp can only do it because it doesn't actually use recursion to do it. So don't use recursion indiscriminately, but that doesn't mean you can't use recursion. And in fact, one of the things that you are free to do is to use recursion on the smaller of two subtrees. So if I have a tree and I want to write some algorithm and somehow it's helpful for me to recurse on one of the two subtrees, well, if I always recurse on the smaller of the two, then something nice happens. Even if the tree is huge, it has like 1 million elements, well, the smaller of its two subtrees has at most 500,000 elements. And the smaller of the two subtrees of that one has at most 250,000 elements. And actually, so even if the tree has n nodes, the depth of the recursion in that case will only be log n. And one of these questions is asking you to do something specifically on the smaller of one of two trees. So that's a place where it can be safe to use recursion. What you do in the other subtree is something else. There you want something like a while loop. Okay. Any questions? Yep.
You said that you can call recursively on the smaller of the two subtrees.
Yep.
How do you know the smaller of the two subtrees if you don't know their size yet?
Well, you can compute all the sizes beforehand using a non-recursive algorithm.
Okay.
So we saw how you can traverse a binary tree iteratively in class. There's even code for it in the textbook. So you can use that to first get all of the sizes beforehand, save them. A map is a nice way to do it, and then you know which one is safe to recurse on. And we'll actually see something today that works in that vein, but is not quite as well. It won't help you on this assignment, but actually it uses the same idea. Okay, so last chance to ask me a question about that. All good? You all know what to do? Okay then.